So last time we talked about the 4.4 undetermined coefficients, but that's a superposition approach. Undetermined coefficients method is to find a particular solution for non-homogeneous linear differential equation. We're talking about the constant coefficients specifically. And we know if we want to solve a non-homogeneous differential equation, linear equation, we need to solve the associated homogeneous equation first. And then we need to find a particular solution for the non-homogeneous equation. And then we just add those two solutions together to get a final answer. So these undetermined coefficients are just for finding a particular solution for the non-homogeneous equation, the original equation we have. And there are two different approaches. We already talked about superposition approach in 4.4. Today we're going to discuss another approach. It's called the annihilation approach. Specifically, we're going to use operators. Okay. So operators, we already discussed before. We used capital D to denote the differential operator, the first derivative operator. But operators can be fact just like an expression for variables. For example, if we have an operator expression d squared plus 5d plus 6, what it means is you have three terms of operators. The first term d squared just means the second derivative operator. You take the second derivative of a function. The second term 5d is just 5 times the first derivative. And the term is just a constant 6. Okay, so this whole as a operator expression acting on any function. Okay, but it turns out that you can actually factor it out as d plus 2 times d plus 3, just like a polynomials or trinomials. Although d squared is not actually, a square. It means the second derivative. You can still factor out as d plus 2 times d plus 3. And what it means is when you apply this operator expression on a function, you can apply d plus 3 first and then d plus 2 to the function. So you take the first derivative of the function and plus 3 times the function. So you get the new function, and then you just apply d plus 2, which means you take the derivative of the new function and plus 2 times the new function. Okay. So that gives us a lot of convenience. When we solve different equations, we can use operators to do it. So let's just talk about some basic properties of operators. Especially, we want to talk about the annihilation operator. Okay, what it means is if you have a function f, the operator expression L acting on this function, if you get 0, then we call this operator annihilation operator. Okay, essentially it is annihilate the function, right? Did I say it correctly? Annihilate, is that the acting the correct pronunciation? Okay, so so how can we find this annihilation operators? All right, it turns out that the differential operator d to the n, which means the nth derivative annihilators each of the following functions. Okay, so for example, you can annihilate a constant by the first derivative. Okay, we know the derivative of constant is 0, right? And you can also annihilate function x by the second derivative. So when you take the derivative of x, you get 1. Then you take another derivative, you're going to get 0, right? Similarly, if you take the third derivative of x squared, you'll get 0 also. So the nth derivative will annihilate all of those functions, 1x, x squared, x cubed up to x to the minus 1. Each time when you take the derivative, you just decrease the power of x by 1. So if you take a derivative n times, that means at the end, all of those functions you annihilate them. Okay, you're gonna get 0 because the highest power in here is x to the minus 1. Okay. And similarly, you can also check that differential operator d minus r alpha to the n annihilators each of the following functions. Okay. E to the alpha x, x times e to the alpha x, x squared e to the alpha x up to x and minus 1 e to the alpha x. Okay. What you can do is just take the operator d minus r each time. Okay. For example, you can apply d minus r alpha to the e to the alpha x. You're gonna get 0. If you apply d minus alpha squared to x times e to the alpha x, you can get 0. If you apply d to the alpha cube on the function x squared e to the alpha x, you're gonna get 0 and so on. Okay. So what you do is just each time when you apply d to the alpha, you just take a derivative of the function and subtract alpha times the function. So you just do it n times for those functions, and it turns out that you're going to get 0 for all of those functions. Okay. So just give you some simple example. For example, when you apply d minus alpha on e to the alpha x, so you take the derivative of e to the alpha x and minus alpha times e to the alpha x, as I said. So when you take the derivative of e to the alpha x, you get e to the alpha x times the derivative of alpha x, which is alpha. So then you get alpha e to the alpha x minus alpha e to the alpha x, which is 0. Similarly, when you apply d to the alpha squared on x times e to the alpha x, this time, you just apply d to the alpha twice. Okay, do it one by one. So let's just apply d to the alpha, d minus alpha time on x e to the alpha x, and you have to use the product rule in this case. But let's just do it step by step. So you got another d to the alpha in the front, and you can distribute the function x e to the alpha x to d and alpha, so you get the d x e to the alpha x minus alpha x e to the alpha x, where d is the differential operator, as we know. So then now we use the product rule here. We need to take the derivative of x times e to the alpha x, but the derivative of x is just 1. So the first term is just 1 times e to the alpha x, or just e to the alpha x. And then we add x times the derivative of e to the alpha x. And we know the derivative of e to the alpha x is just alpha times e to the alpha x, as we already did. So then the second term becomes x times alpha e to the alpha x. And then we just subtract alpha x e to the alpha x in the third term. And you can see the second term and the third term, they just cancel. So it just becomes d minus alpha acting on e to the alpha x, which we already did in the first example, and that's just 0. That's just 0. Okay. So you can also check any power for d to the alpha and to those functions. You just get 0 at the end. Okay. So that's d to the alpha to the n and dn d to the n. We can also use the differential operator d squared minus 2 alpha d plus r squared plus beta squared to the nth power to annihilate each of those following functions: e to the alpha x cosine beta x, x e to the alpha x cosine beta x, x squared e to the alpha x cosine beta x, up to x to the minus 1 e to the alpha x cosine beta x, and e to the alpha x sine beta x, x times e to the alpha x sine beta x, x squared times e to the alpha x sine beta x, up to x and minus 1 e to the alpha x sine beta x. In other words, this operator d squared minus 2 alpha d plus r squared plus beta squared to the n will annihilate a bunch of functions in the form of x times some power of e to the alpha x times cosine beta x or sine beta x. Okay, up to the power n minus 1 for x. All right, and this can be also checked just like we did for the d minus alpha to the nth power. You're going to get 0 in all of those cases. So we're not going to repeat that. It will be a little tedious, but that's true. Okay, that's a fact. So let's just do some examples to find a differential operator that annihilates some functions. So we have 3 functions here: 1 minus 5x squared plus 8x cubed in part A of question A. Question B, we have an exponential function e to the negative 3x, and in question C, we have 2 exponential functions, 4e to 2x minus 10x e to 2x. So you just use the rules we just had. Okay. So in the first question, we have a polynomial of degree 3. Okay, so all the terms are polynomial functions, or each term is a power function or integer power. Okay, positive integer power, and we know the operator d to the n will annihilate all of those power functions up to x to the minus 1. So if you just let n equal to 4, then d to the 4 will annihilate all the power functions of 1x, x squared, x cubed. Okay, as long as the power is less than 4. So that means we can use the operator d to the fourth to annihilate this function, all the terms. Okay. So the operator, the answer will be d to the 4. Of course, you can also use d to the 5 or d to the 6, but the d to the 4 will be the smallest power of the differential operator. Okay. In question B, we have a exponential function e to the negative 3x. So if you compare the operator d to the alpha minus d minus alpha to the n, and you let n equals 1, okay, then that will annihilate e to the alpha x, okay. So so we can let alpha equal to negative 3. So that means if we apply the operator with d minus negative 3 to the 1th power, first power, it will annihilate e to the negative 3x. So d minus negative 3 is just d plus 3. So the operator we find is just d plus 3. That will annihilate e to the negative 3x, right? Okay. In the third question, we have two exponential functions, but they're all of the form, x to the minus 1 or x some power times e to the alpha x. So we have two terms, but if you let n equal to 2, then we can annihilate the functions of e to the alpha x and x to the 2 minus 1, which is x, times e to the alpha x. Okay. So if you let the alpha equal to 2 and n equal to 2, then we just get the d minus 2 squared, right? And that will annihilate each term of the function f, okay? Both e to the 2x and the x times e to the 2x. So the answer is just d minus 2 squared, all right? So that's the second example. Let's just do another example, okay? This time we need to verify that the given differential operator annihilates the indicated functions, okay? So the first operator is d squared plus 64. And then the function is y equal to 2 times cosine 8x minus 5 sine 8x. Okay. So we're talking about the third operator, d squared minus 2 alpha d plus alpha squared plus beta squared to the n. One of those special cases, just to verify this annihilator will work on this function. Actually, that's the only question we have for this problem. Okay. So we can use this third rule. So in this problem, if you let alpha equal to 0 and beta equal to 8 and n equal to 1, then the operator arrow, which is d squared minus 2 alpha d plus alpha squared plus beta squared to the n, will be what? D squared minus 2 times 0 times d plus 0 squared plus 8 squared to the first power. Okay. If you let those alpha, beta, and to those numbers. So 2 times 0 is just 0. And at the end, if you simplify the whole thing, we just get d squared plus 64. Okay. Right? So now we just apply this operator to the function. Let's just check it specifically on this function. So d squared plus 64 acting on 2 cosine 8x minus 5 sine 8x. So we can just break into two terms. We have d squared acting on this function and 64 times this function. So that means we're going to take the second derivative of this function and then plus 64 times the function. So you just take the derivative 2 times on the function in the first term. So if you take the derivative cosine 8x, you're going to get the negative sine x, 8x times the derivative of 8x, which is 8. So we got the negative 16 sine 8x in the first term. And if we take a derivative of sine 8x, we're going to get this cosine x, 8x, times the derivative of 8x, which is 8. So then the second term just becomes 5 times 8, which is negative 40, times cosine 8x. And you can also multiply 60 out, or distribute the 60 out on this function term by term. So we're going to get the 64 times 2, which is 128 cosine x minus 64 times 5 sine x 8x, which is 320 sine 8x. And then we need to take the derivative of negative 16 sine 8x minus 40 cosine 8x. So once again, if we take the derivative of sine 8x, we get cosine 8x times 8. Negative 16 times 8, you just get a negative 128. And if we take the derivative of cosine 8x, you get negative sine 8x times 8. So the second term just becomes negative 40 times negative 8, which is positive 320 times sine 8x. And then we still got 128 cosine 8x minus 320 sine 8x. You can see all the terms cancel. Okay, so you get 0. So it does work. So we already checked this differential operator annihilates the function. But let's just consider, some special case. When alpha is 0 and equals 1, okay. Okay, just look at the operator d squared minus 2 alpha d plus r squared plus b squared to the nth power. If you let alpha equal to 0 and equals 1, so this will become d squared plus 2 times 0 times d plus 0 squared plus beta squared to the 1, first power. So it's just the d squared plus beta squared. Okay, we got the some zeros in here. Then what? So now let's just consider the function x to the minus 1 e to the alpha x cosine beta x. When alpha equals 0 and equal to 1, we just get the x to the 1 minus 1 times e to the 0 times x times cosine beta x. 1 minus 1 is just 0, x to the 0 is just 1, e to the 0x is just e to the 0, which is 1 also. So at the end, it just becomes cosine beta x. Similarly, x to the minus 1 times e to the alpha x sine beta x. When alpha equal to 0 and equal to 1, we get the x to 1 minus 1 e to the 0 to the x times sine beta x. Again, we get the x to 0, which is 1, and the e to 0, which is also 1 in the front. So that's just sine beta x. So then, you apply the operator d squared plus beta squared on this cosine beta x, sine beta x, you should get 0 according to the rule in here. All right, because this operator d squared minus 2 alpha d plus alpha squared plus beta squared to the nth power will annihilate all of those functions. And we just consider, the special case of alpha equal to 0 and equal to 1. Okay. So according to the rule, this operator d squared plus beta x squared should eliminate cosine beta x and sine beta x. And you can also easily double check it. Indeed, you get 0 if you apply this operator, either cosine beta x or sine beta x. All right, just like we did in here. So this is just some simple examples of annihilators. Any questions on these examples?